Objective of the experiment is to study and obtain waveforms for frequency modulation system. Today we are going to perform two experiments. One is FM modulation and other one is to study and obtain waveforms for frequency demodulation system. So we are going to perform FM modulation, frequency modulation and frequency demodulation. Since the kit is common for both, so we are performing both the experiment at the same time. The apparatus we are going to use today are this kit, ST2203 frequency modulation and demodulation trainer. This particular kit is it is acting as a prototype used to modulate and demodulate the FM signal. When we ever listen frequency modulation or FM, the first thing comes to our mind is the FM channels that we used to hear every day. The FM channels having a frequency range of up to 108 megahertz. So if you remember any two channel, then there will be a guard band between these two, any two channel frequency, minimum guard band. If you consider big FM 92.7 megahertz and red FM 93.5 megahertz, so you will come to know there is a minimum gap of 800 megahertz in between these two bands. So minimum requirement of guard band, so that interference can't be there. If you ever tune to FM radio, then once you tune it in between 92.7 and 93.5 red FM, then you come to listen both the channel. So you come to listen music from both the channels. So minimum guard band of 800 is required in between any two channels. Okay. Our Jamia has also an FM frequency. You can search whatever the frequency is. What we are going to do when there is FM in real scenario, then we have an audio signal that needs to be frequency modulated and sent, so that every receiver can receive tuning to the particular frequency and come to listen to that particular information broadcasting from that frequency. So when there is an application of FM in real world in application based systems, then we have music or any information or traffic updates or news or any commercials. So we have the data actually that we need to transmit. But mostly or in FM we have the data in form of audio signal. So when we are performing it in the lab, so we need to generate an audio signal. So first of all we need an audio oscillator here. You can see audio oscillator here. Here is audio oscillator where we are going to generate an audio frequency that will act as input signal or modulating signal for modulation. So here we are going to generate this audio signal using this audio oscillator. There is output written over here. So from there we can take audio signal from this audio oscillator. That particular signal we are going to give it to input of modulator circuit. You can see this is a modulator block. This is a modulator block. You can see modulator circuit. Here we need to give audio input. We are going to give this output here. When we are going to do connections in some time, we will connect this output audio signal to audio input, so that we are giving this particular signal that needs to be modulated. Okay. When we are doing frequency modulation, then as per instantaneous value or amplitude of the modulating signal, the frequency, instantaneous frequency of a carrier wave is going to change. Wherever the amplitude is maximum, we are going to consider a sinusoidal signal of audio frequency. So wherever the amplitude is maximum, the frequency of modulated wave will be maximum at that point, and the frequency at the lowest part of modulating wave, the amplitude where the amplitude is minus VPP, the frequency of modulated wave will be minimum. So the waves will look, we'll see how the modulated wave look like. So here we have modulation circuit. Now we will power it up and do the connections and see. And in apparatus thing we are using these connecting wires, and so here we want to see the input signal as well as the modulated output on a same channel. So here we are using DSO, and we are going to use both the channels. You can see two ground and reference lines here. One is yellow for channel 1, and the other color is sky blue, that is for channel 2. So here we are using both the channels. As I told you in earlier practicals, that these knobs are used to adjust the voltage level or amplitude level of the signal. So if I turn it right, then amplitude will get increased. If I turn it left, then amplitude level will get decreased. This is for channel 1 and this is for channel 2. So for for amplitude adjustment of channel 1, I need to use this knob, and for amplitude adjustment of channel 2, the blue color, we need to use this knob. And this is a time scale knob. So for adjustment of time period or time scale, time per divisions, we need to use this. Okay. So this, here we are using both the channels. At channel 1 we are going to connect the input. So here we are using audio signal. So we are going to use channel 1 to see how audio signal looks like here, that we are going to give input here. I'm using this black probe to 0 volt. I'm connecting this to 0 volt ground, and I'm going to see the output of this audio oscillator, so that we can see how our input signal looks like. I need to power it up. I am powering it up the kit. Now power is on. Now I am going to connect here, so that we can see how the output of audio oscillator looks like, and that is the signal that is a modulating signal. This is the information we are going to transmit or modulate using frequency modulation technique. This is the signal containing real information. So here we can see, if I run this, because it is stopped so that it is not showing anything. If I run this, you can see the at channel 1 we can see easily the audio signal of sinusoidal nature. I'll stop this so that we can see it clearly. You can see this. This is an audio signal that we are going to give here as an input, and that particular signal we are going to modulate. You can see there is a crest and trough where the amplitude is maximum. As per frequency modulation technique, the frequency will be maximum here. So the after modulation, the modulated wave, after modulation, the modulated wave will have maximum frequency here. It means the waveforms will be closely spaced here, where the amplitude is maximum, and where the amplitude is minimum, there will be a space between the waves. Actually, the carrier wave is going to get modulated as per instantaneous value or the amplitude of this information signal or modulating wave. The properties of carrier wave is going to get modulated, that is getting generated in modulator. So I am going to do connections. This I'll keep there so that we can see how our input signal looks like. We have shown it on channel 1. Now I am connecting this output, the audio signal that we are getting from here, audio oscillator, to audio input of the FM modulator. Okay. Here we have knob for two modes of modulation. One is the reactance mode and another is varactor mode. The varactor, when we are saying, then it is a variable capacitor. You would have known that a capacitor in reverse mode, or a diode, varactor diode in reverse bias mode, changes the voltage value as per amplitude of the particular signal. So I am going to show you how the modulated wave look like. Here we can directly see the modulated wave very clearly. If I connect it from here, voltage control oscillator is a circuit inside, so we can see the modulated output from here. So I am connecting this to channel 2. This black probe, this is a probe for channel 2. I am connecting this ground here and this particular thing, so that we can see how the modulated wave look like. So I'm connecting it here, and I'll run the CRO so that we can see how the modulated wave look like. You can see over here, if I run this CRO, I need to adjust this. You can see here I need to adjust a bit of its amplitude so that we can see it clearly. Once I stop it, you can clearly see how it is like that, whatever I was saying. You can see somewhere the frequency is more or higher, the waves are closely spaced, and at some point the frequency of the carrier wave is minimum or lesser as compared to this particular section. So as per amplitude, where the amplitude is higher of a modulating signal, the frequency of modulated wave is more, because the deviation in frequency modulation is plus minus 2 delta f. Delta f deviation is there, so plus delta f and minus delta f is total deviation is 2 delta f in frequency modulation. So this here as per fc gets added with delta f, so the frequency here we are getting fc plus delta f, and here we are getting fc minus delta f. So the you can easily see that this wave is a frequency modulated wave. As per amplitude of the modulating signal, frequency of this carrier wave has got changed, and the frequency of carrier wave is maximum where the amplitude of modulating wave is maximum, and as per the amplitude of modulating wave, the frequency is getting changed, or instantaneous frequency is getting changed. So we have modulated the signal using frequency modulation technique, and this is the way the frequency modulated signal look like, and it contains the information of a modulating signal. Whatever information, whatever the audio signal was there, it is being incorporated in this carrier signal, because as per the variation of amplitude of that particular signal, this carrier signals frequency, instantaneous frequency is getting modulated, so information is in there. So I'll do the connection so that we can perform the demodulation part. I'm connecting this as here, as we have connected. Now when we see demodulation part, this particular block is for frequency demodulation, right? In our radio or television, there is a frequency modulation, frequency demodulation. In our radio, we need to tune it to the particular frequency so that we can get that particular frequency or the information broadcasting from particular station. So here we have amplitude limiter. In a real scenario, when signal is getting transmitted, you can see here actually the amplitude of a modulated wave is constant. Amplitude is not changing, only the instantaneous frequency is changing. The amplitude is same, but when we transmit it through an antenna into the environment, there will be a noise or any other distortion in the signal. So sometimes this amplitude gets more, something gets added up, some other signals get added up. So we need to limit the amplitude so that unwanted or unwanted signals from this particular signal, modulated signal, gets clipped off. So we need to use amplitude limiter. You can see this block is amplitude limiter. So first of all, we need to give the FM output to input of this amplitude limiter, so that we can limit the amplitude and clip off the unwanted signal that might have come in contact with our transmitted signal. So whenever it is being used in real scenario, then there will be an antenna after this transmitter block, and we transmit that particular modulated signal into the environment, and at the receiver end we have detuned circuit to detune it, and we have antenna, receiving antenna also, but we are performing it in the lab. So this kit is a prototype in order to see how frequency modulation and demodulation take place and how the waves look like. So we are verifying this, and our objective is to see what is frequency modulation and what is frequency demodulation and how they are done. So we have both transmitter and receiver at the same part. So we are going to assume that whatever we are transmitting at transmitter part, we are receiving the same at the receiver part. So I am connecting this FM output that is the transmitted that we need to transmit that particular signal through an antenna. So here we are using it on the same kit. So I am connecting this output to the input of amplitude limiter. So we have connected this, and thereafter we need to there are so many methods for frequency demodulation technique. The generally used is quadrature type or slope detector type frequency demodulation. In quadrature type we used to get 90-degree phase shift. You will come to know when I'll show you the demodulated wave. Here we are using the quadrature type, so we are going to get a 90-degree phase shift of demodulated signal. When I say 90-degree phase shift, it means where there is peak of amplitude in the input signal, we are going to get negative peak or crest in or trough in the demodulated signal. And after detuning it using the resonance circuit, we are detuning it. You can see detuned resonant circuit it is. So we are going to give that particular output of this amplitude limiter, because first of all we are limiting the amplitude, we are removing the unwanted signals, we are clipping off the unwanted signals above the threshold level because noise might have added up. Here we don't need it, but we are using it so that we can remove any other thermal noise that is going to come here. So I am going to connect output of this amplitude limiter to the input of detuned circuit. Here we are going to, as I have told you that there is a frequency deviation of plus delta f in frequency modulated wave. So there is a center frequency fc and variation of plus delta f and minus delta f. Total variation is 2 delta f in instantaneous value of a frequency of a modulated wave. So we are going to clip off the offset or nearby variation of frequency. So we are going to tune it to center frequency. That's why we are using detuned resonant circuit. So I am going to connect the output of this particular amplitude limiter to input of detuned resonant circuit. This particular circuit we are performing is for demodulation. We are doing demodulation. We are going to see whatever audio signal we were transmitting from the transmitter part, we are going to receive the same at receiver part with 90-degree phase shift. As I told you, the quadrature system of demodulation gives 90-degree phase shift. We will see that what I am talking about. So whatever information, whatever audio signal, whatever music, whatever commercial, whatever traffic update, whatever be the information in this audio signal that we are considering here as a message signal is going to get retrieved at receiver part. It means the information is getting conveyed or the communication has taken place. So I am going to connect this particular output of this detuned circuit so that the center frequency has got adjusted. Here we have taken care of amplitude variations. Here we have taken care of frequency variations in the transmitted signal from center frequency. We are adjusting the frequencies to the center frequency. Now I am connecting this output to a low pass filter, because whatever the audio signal we have given over here, if we are using a low pass filter, so that the higher frequencies are getting stopped and we are getting the lower frequency, the audio signal frequency that we have transmitted where the information is, so the wave will get demodulated as the audio oscillator generates a signal of audio frequency where the information is. So we are using low pass filter to pass that particular audio signal and clip off the higher frequencies of due to the carrier wave. So I am going to connect output of detuned circuit to a low pass filter. Now this output we are getting after low pass filter. There is an amplifier used here. The gain is adjustable. We can adjust the gain if I move it rightwards, so I can change the gain of a received signal. Here we are getting the demodulated output. So this output must be similar or containing the same information that was contained in the message signal. So we are going to get the same audio signal here also. The audio signal, the message signal that we sent, we are going to retrieve that particular signal. So we have performed the demodulation. So we are going to see how this signal look like. I'm using the second channel, the channel 2 for demodulated wave. You saw that this, I have stopped this DSO, so it is showing this message signal here, the audio signal. This is the signal, original signal we are sending, we are transmitting, and this is the modulated wave. This is a FM modulated wave. So when you prepare the report, your first result is this, where you will show the modulating signal, and here you will show the FM modulated wave. This is the first experiment result, where you need to show this is a modulating signal and this is the FM modulated wave. Now we are doing demodulation, where I am going to connect this particular channel, blue channel, or the channel number 2, this probe to the output of demodulator, so that we can ensure that we are going to receive this particular information and we have decoded the particular information, or we have received the audio signal that we sent as a message signal. So I am going to connect this black probe of this to the ground. Here we have the ground, and I am going to connect this red to the output of this. I'll use some connector here also. I'm going to connect it like that. This is the output. I am going to see our DSO is at stop mode. I'll run that so that you can see we have retrieved that particular signal. I'll pick it up. When I stop it, you can see there is a phase shift of 90 degree. Where there is a peak of this, we are going to get a lower peak of this. So there is a 90 degree phase shift here. As I was telling you, there is this, you can see the blue channel. If I adjust this gain, if I increase this gain, you can see the blue wave, amplitude of the blue wave, that is the demodulated wave here, is going to increase. First of all, let me adjust amplitude here so that it can become short. Now I am adjusting this. I am turning it right. You can see the amplitude of blue wave. If I stop it, you can see as it is dynamic, so it is flowing. When I stop it, then you can see it clearly. This is a this is a modulating wave. The signal that was having information or containing the data or music or speech, and this is a demodulated wave. So these both waves are same, so we have retrieved the information that we sent using FM modulation. So this is a FM demodulated wave, and this is the message signal. You can see 90 degree phase shift. We can adjust this, or we can reverse this phase by using an inverting amplifier as a buffer. We can reverse it into the original phase. What I was trying to show you, if I adjust this knob, you can see the present time amplitude of this signal, the blue one. If I adjust this, you will see the change in amplitude. I am just putting it to run so that it will continuously run. Now I am changing this. I am changing this gain so that you can see the amplitude of that signal will going to increase. You can see that there. You can see on the DSO that amplitude is getting increased. If I am decreasing, then amplitude is getting decreased. So this is for adjustment of gain at low pass filter, if there is any amplitude distortion or amplitude is getting reduced because of the demodulation circuit, then we can adjust the amplitude from here, from a low pass filter. Here we have an amplifier that can amplify, having a gain, so that we can amplify the amplitude of the demodulated wave. So you can clearly see here that we have retrieved the wave, the information from the modulated wave, and we have got the demodulated wave exactly same as the particular message signal. This is a modulating wave that we need to transmit using FM modulation technique, and this is the FM demodulated wave. So we have achieved demodulation because we have got the same wave here at channel 2. So with 90-degree phase shift, that I told you how it can be handled easily. So this is the circuit we have. We have produced an audio signal from using an audio oscillator. We have given that particular audio signal as an input to FM modulator circuit, where modulation took place, and after we got the modulated wave, we saw that how modulated wave looks like as the frequency of the modulated wave is getting changed. So characteristic that is going to change for carrier wave is frequency as per amplitude of the modulating signal or message signal. So this is a frequency modulation. So we have achieved the modulated wave, and after that we demodulated it. First of all, we did amplitude limitation, so that any changes or unwanted changes in amplitude can get handled. Thereafter we use this output of amplitude limiter to detuned circuit, so that any deviation from center frequency can be handled, and thereafter output of that particular detuned resonant circuit to input of a low pass filter, so that we can perform demodulation and we get the exact particular message signal or a wave that was containing the information. So here you can see, when you prepare a report of demodulation, frequency demodulation experiment, then you have this result you need to draw, or you need to include in your report. This is a modulating signal, and this is frequency modulated demodulated wave. So this was our experiment, completely frequency modulation and demodulation. In your lab manual also you can see, this is experiment number 3, frequency modulation system, and experiment number 4 is frequency demodulation system. So we have today we have performed 2 experiments. You can read other data from the manual also. Manual is quite lengthy and everything is explained. So this is what frequency modulation and demodulation is. When it is used in real application, then music or audio signal is getting modulated using frequency modulation technique with a frequency modulation technique, and it is getting transmitted using an FM antenna, and at receiver end we use detuned circuit or and receiving antenna, FM antenna, and receive that particular information and decode that, demodulate that particular information, and we used to hear the same music or same news or same commercial or same traffic update from that particular station. So this is the circuit for FM modulation. These are the connections. You can include apparatus and the equipments in your report, and I have shown you the result of that modulation experiment also and demodulation experiment also. So this is our experiment for experiment number 3 and 4. Thank you.